Hi, my name is Alan Davis, and I am a reporter for the Rankine cycle experiment that we ran. So, basically I'm going to go through what our objective, the purpose of this was, some brief background and equipment and what we did. And then I'm going to get into our data analysis, the results we got, the efficiency of the components of this cycle, some general observations, and what we can conclude from this presentation. So, to get started, the whole point of this was to understand basically the operations that happen in the Rankine cycle. We needed to measure relevant data in order to figure out the efficiencies of the components in it, and also for that we'd have to calculate the specific enthalpies at different states in the process, which we were given, or rather which we measured through observations and sensors that were part of the experiment. So then from using these, we can observe the performance and general behavior of this simplified, not too efficient cycle. So the background. The Rankine cycle is a process of combustion to produce electric power. And it starts when water is pumped into our boiler. From there, the boiler heats it up to where it's a superheated vapor. From there, the steam is directed through a turbine, which is connected to a generator to generate electricity. And then the steam is condensed back into water and thus finishes the cycle. The cycle repeats itself. So for the equipment that we actually used here, we have a small condenser tower. And from here we start with the water goes into the boiler. The boiler heats it up. It's going to go into the turbine and generator right here. And then from there the water is condensed and turned back into water here. And we should be monitoring key points of this experiment using the virtual interface right there. And to power the boiler, we're using propane. So liquid propane source right here, which is actually what our input is going to be for the cycle. So in the ideal cycle, it works like this, where you pump it up to a high pressure, you expand it, so it boils here from water to a superheated vapor. The turbine is here, it drops the temperature. It's where we actually get our energy out of. And then in the ideal cycle, which everything was not completely connected, this was a simplified model, then you would pump it back here. So, and basically decrease it when you condense the water vapor back into water, where you can then repeat the cycle by boiling. So some of the relevant equations we're going to have to use in our data involves efficiency, which is the work that we're doing over the heat that we have to put in. So the heat that we put in is the propane that we're burning, and the overall work of the system is going to be the electricity we generate. But we can also look at this for individual components of it, such as the heat that goes in and is taken out of the each component, or the heat that's generated as opposed to what we had to get in for that relevant part. Specifically the turbine, the generator, and the boiler for our simplified case. Also for any of these we need the mass flow rate, so what we did is we took the total amount of water that passed through the system throughout the cycle, then we divided it by the total time. Because it should be operating steady state. As we'll see, that's not exactly the case. So just from some initial data, the boiler is supposed to maintain at a constant temperature. It's just boiling water. But this cycle was not entirely efficient. So what actually happened is the boiler started to heat up as time pressed on. Possible reasons for that include that water vapor was staying in the boiler and not continuing to the turbine, which hurts efficiency right there. But you would think that a higher temperature would mean that a higher temperature on the turbine might increase power for increasing temperature. But it also makes the system less stable, as we can see by some of the notable dips in here. And the outlet temperature also increasing, as we can see here, means that it's not taking out necessarily more heat than was actually, than it would be just, you know, at steady state. And also, from these jagged edges here and here, the system's less stable. It's not designed to do this, and it's actually going to decrease the efficiency, which is shown by that if we increase the heat that we're using from the boiler right here, which is our input from burning the liquid propane, the RPMs of the turbine should increase, and they don't because it's only set up to handle a certain speed anyways. So these are some notable dips before we even get into calculations to show some issues with our efficiency. So into our actual efficiency analysis, we looked at the heat flow out of the boiler and then the energy that came in from ideal liquid propane combustion, which is actually about 10% less than this if you aren't willing to wait for everything to go to steady state. But at the same time, an ideal system would, you know, take all the energy out of it and not increase, you know, hot air coming out, steam that gets stuck in the boiler, etc. So these things added into our efficiency of only 25.4%, strictly in the boiler alone. So then with the turbine and generator, we had increasing issues with our efficiency because the work rate from the generators and what it should be putting out from the heat difference in the enthalpies going into and out of the generator is here, but the actual output was only, once again, about 25% of that. So these are our main cycles actually for calculating our overall efficiency because they include both our input values and the actual output that we get through the electricity from the turbine to the generator. So with the condenser was supposed to condense the steam all back into liquid water. But it didn't actually condense near as much as it should have been, so it shows that we had a lot of losses throughout the entire system for that. And we also didn't have values measured directly in and out of the condenser, and the values we got leaving the turbine suggested the water was already starting to condense again before it reached the condenser. So that's more losses in the tubing, the pipes, and even in the turbine. So we were losing a lot of our water before it had even gone all the way through the turbine. And so the condenser itself had an efficiency of slightly under 20%. So then the total system efficiency, which is based off of our input heat and our actual power output, ended up being around 5%. So this is pretty far from that ideal system that we showed earlier. So some of the sources of error which have been discussed involved that we had undefined starting and ending states. Those weren't specifically measured. The system itself was inefficient. The parts themselves were inefficient. The components, as shown by just measuring individual ones, were 25% efficient at best. And we also found a reasonable amount of thermal noise in the system from our individual measurements. It showed almost like oscillating powers, so oscillating numbers, always around the same value, but the oscillation suggests that there was a lot of noise in the system, which would make it less stable. And so our conclusions, this is obviously a very inefficient system. We could use more measurements, specifically at the end of the condenser and before going into the boiler, would increase the accuracy of the measurements themselves. And the boiler heating up, as we mentioned in the plots, has led to less efficiency and less stability, a lot of thermal noise, and very high thermal losses. And the assumptions that we had to make from our measurements also increased the uncertainties of the calculations. So, any questions?